We are a little bit out of sync with respect to the days explained into the handouts which you have. I hope it's not that terrible. We will anyway start from where we stopped yesterday. And yesterday we were talking about system-level frameworks and tools which we can use in order to explore different aspects of the hardware-software co-design receipt. I have spoken quite a lot about open hardware frameworks and especially about HiPEAC, and we just started something which is at a higher level of abstraction, which doesn't imply a direct path to hardware implementation, and is called Gen 5, and its derivatives such as Gen 5X. Today we will see how we can use in practice Gen 5X to accelerate workloads in different ways, including computation and communication. And since we are looking at how technology can help us, we will look at how we can incorporate advancement from the technology levels in order to abide to application characteristics, in particular for the case of machine learning. So we will talk about systolic arrays, analog in-memory computing, compute near memory, inter-chiplet communication using wireless links, so short-range wireless links, and if we have any time, we will look at thermal issues and something called fuel cell arrays. So without further ado, just a recap, what is a system simulation framework in something which allows you to specify a virtualized system which lives as a virtual machine and has the characteristics which are specified in a configuration file. Then you can spawn an entire operating system onto that, connect to this virtual machine, launch applications, and do some profiling. This is how it works. You can just define a configuration, like caches, number of processor, speed, etc., connect to the system, and then just say, okay, here I want to start my profiling, and there I want to see what are the profiling informations. And for every component which you specify for your system, you have what are the characteristics such as ACACES, number of clock cycles in which the component is active, if it's a cache, it's a misses, and so on and so forth. Now, before we look into one particular accelerator solutions for that type of environment, in system simulation frameworks, every component is modeled in an abstract way. So it is very easy to fool yourself when doing this type of explorations, because these type of frameworks, they have no idea if what you're doing is reasonable or not. You can very easily define an accelerator which does a lot in 0 time, and the simulator will have no problems with that. It is your responsibility to do the due diligence and the hardware validation so that you know that what you're simulating actually is real. For the first example, which I'm going to show you, we're talking about a digital implementation, so we have characterized that using Verilog, and we extracted area, power, and delay numbers from that. For the second example, we will talk about analog computing crossbars, and for that we have to rely to an external collaborator, which is IBM Research in Zurich, where they have a very advanced research in the fabrication and characterization of analog crossbars, so we could have real data from them. It's in any case key to have some real data to start from. Sorry for the pretty long introduction, so let's go into it. So what is TICSAT? TICSAT is tightly coupled systolic accelerator for transformers. What it is basically in the name, it's a systolic array which is tightly integrated to our system, so it acts basically as a customized functional unit, and we want to use it to accelerate transformers. I will not spend any word on what transformers are. I think that all of you know more than enough about it, and most of you know even more than me. What it is important is that, as with other machine learning applications, there's no other way in complexity of transformer but up. They just get more complicated with more parameters, with more required operations, and so on and so forth. The other characteristics, please mute your cell phone, is that before I said that in feature extraction framework, tool flows, what we have is that 10% of the code takes 90% of the runtime. For machine learning is even worse, and for transformers is even worse. So this is a little example which we did for a standard transformer, which is very large on a fairly common architecture. And 99.97% of our code was spent during exactly one kernel, which is the matrix-to-matrix multiplication, which gives kind of an obvious target for what we really want to accelerate when we're talking about transformers. And the way to accelerate a matrix-to-matrix multiplication is, since 1982, systolic arrays. So this is the oldest paper which I was able to find talking about systolic arrays. If you know something older than that, just let me know. I really love this historical perspective on things. And the way systolic arrays were defined back then was kind of generic. It was a machine in which data was pumped in and out. It turns out that one particular implementation of a systolic array is very good in implementing matrix-to-matrix multiplications. And this has given a lot of interest in recent years because basically machine learning. And the first implementation of systolic arrays were basically meant for server farms, cloud computing type of things, but more and more, even for the edge, we can see commercial implementation of what Google calls tensor processing units, and basically inside them you can find systolic arrays connected to fast memories. So, how does a systolic array work? It is composed by a two-dimensional mesh of cells. In each cell we have 3 registers, 1 multiplier, 1 adder. Then we need a bunch of FIFOs in order to skew the input data and skew the output data. If you just do the math onto this connection, you see that by storing the weights inside the weight register and keeping them constant, then we can stream in a stripe of inputs and compute a stripe of outputs at the output. So it is a very simple and very compute-intensive type of accelerator, and the basic implementation of something like this can be done maybe in a few days. Then the devil is how to integrate that, how to optimize it, etc. But the main machinery is very, very simple. Hopla. So how did we integrate that? We wanted to integrate inside the processor as a customized functional units. Gen 5, and in particular Gen 5X, provides hooks in order to specify extensions to the instruction set. What did we need? We needed a way to specify the fact that we are looping weights inside each of the cells of the systolic array. Then we needed a further instruction to program a part of the input register and read out a part of the output register and do basically nothing else. And then we need an instruction which programs a part of the input, read backs a part of the output, and enables one cycle on the systolic array. So when we issue input-output compute, what happens is that the systolic array advances by 1 step, both in the horizontal and in the vertical direction. Why do we need both this? Well, this is because usually the bandwidth which you have in the pipeline of a processor is smaller than the bandwidth which is required by typical systolic array. So we need to find a way to just partially fill the input buffer, and when we are finished filling the input buffer, only at this point we can advance the computation of the systolic array. The other question you may have is, so at the very beginning, what do I read out? Because, you know, all these FIFOs, the registers, etc., they imply a delay. The answer is we don't read out anything. We can just discard the values which we read out, and at the very end, whatever input we put into the systolic array is basically meaningless. We can just pad the input and output, but we will see that this is not that bad, both from a runtime and an energy perspective. Indeed, we tested that, and we tested that using a fairly lightweight machine, so single core, 1 gigahertz, a few kilobytes of level 1 cache, a little bit more of level 2 cache, etc. So this is kind of the model of an edge machine, but is not the system on chip, few kilobytes type of machines, which we're looking at in the first couple of lectures. And this is because system simulation would be actually an overkill for those type of simple, ultra-low power systems. Here, we're looking at a higher level of abstraction, which allows you to have a higher level of complexity in our simulated systems. And we look at systolic arrays, and C2 is kind of the public name for the systolic array of different sizes. So what we found is that, supposing that in our matrix-to-matrix multiplication, we may have 8-bit inputs and 8-bit outputs, and that the bandwidth in the processor pipeline is 32 bits, just by using a 4x4 systolic array, we can have a speed up of 2x. So this is how you should interpret this. This is the naive implementation of the transformer code. Here we try to optimize as much as possible using tiling, using data reuse, but still at the software level. And here we started to accelerate in hardware. So with 16 multipliers, 16 adders, we already had a 2x. I would say that these are 16 multipliers and adders well spent. And if we have more area, we can invest more, we can just scale up these operations. How much? Well, actually, we stopped at 16 times 16 because we thought that it was not reasonable to have more than that as a custom functional unit in a processor pipeline. Nonetheless, even at this level, we have that matrix-to-matrix multiplication is still 97% of the runtime. So if we wanted to scale more, the next thing that should have been accelerated would have been still matrix-to-matrix multiplication. Okay, so another thing that we wanted to look at is okay, we have a spatial accelerator. Yes, please.
Sorry, one thing. With the accelerator, you are accelerating just the computation in itself. Do you also make something for memory access and the other, or?
There it is.
Perfect.
So the question is, what about memory and memory arrangements? And yeah, thank you so much for introducing the next slide.
Sorry.
No, that's okay. That's perfect. So how does tiling work? So if we need to do a matrix-to-matrix multiplication and we have to compute this output tile, what we need is this stripe at the input and this vertical stripe for the weights. Okay? So what we may do is to organize our computation so that we do the computation of partial outputs while diminishing as much as possible the rewriting of the weight registers, because these actions are basically overhead, and we would like to do that as little as possible. Which means that as we are processing inputs tile by tile, we are not accessing our data in memory in a completely linear way. But as we proceed, we have to jump from some memory addresses to some other memory addresses if our matrix is stored linearly, row-wise in memory. Because in this case, we have to access these elements, then these elements, then these elements, then that elements. So every time we change row, we have a jump in memory. Or do we? Well, we can just arrange our matrix in memory in a proper way so that we have the access pattern that we want, and this access pattern becomes completely linear. We did that, and it turns out that by properly arranging inputs in memory, we can reduce massively the number of data cache misses and level 2 cache accesses. Keep in mind that this is in logarithmic scale. And this results in very noticeable speed up in the system which we actually simulated, which again is the same as before, and is, we think, a reasonable system for edge computing. So much so that if we do proper data layout in memory, we have better performance than actually doubling the accelerator resources. So from here to here, we are doubling the size of the accelerator, which means making it 4 times bigger. From here to there, we are not modifying the hardware at all. So this is an optimization which has exactly 0 cost. Almost. Because the moment in which we organize the input arrays, input matrices in a tile way, then we input also other pieces of computation, which we have to perform in transformers, but these little pieces of computation are either non-affected at all, or they are so marginal that they have no impact whatsoever in the grand scheme of things. Again, we did further experiments. So here, instead of increasing the systolic array size, we increased the number of processors which we have in the system, and each processor has a custom functional unit. Results are basically the same. There is much more in this paper. Alireza Mirshai, which led this work, really liked to experiment around, so we will find a lot of results there. Yes?
So when you sped up your memory by optimizing your memory layouts, it seems to imply that the accelerator is kind of just sitting there waiting for a long time.
Sorry, he's going to?
So your accelerator is just waiting in that time period, not doing anything, right?
The data layout in memory is not done dynamically. So you can store the data where it is needed. Having said that, when you are processing, so this is a custom functional unit, so it lives in the processor pipeline, and yes, it has to abide to all the cache misses which you may have, and so on and so forth. But by doing this tiling, you are actually minimizing the overhead of the cache hierarchy. Yes?
So the data that is stationary in your systolic array is the weights in this case, right?
Yes.
So, okay. So is that because you're using your expensive transformers, or is it because it's the best?
I think it's a very reasonable arrangement, because you can have your weights in a tile inside the systolic array, and then streaming an entire stripe of inputs. So the tile is much smaller than the actual dimension of the matrix. Having said that, I don't have comparative results with output stationary solutions. I guess the result will not be that much different, but I don't have hard data to support that, I'm sorry. There is a difference between an intuition and the results. I try to make it very clear. Yes?
Okay, the accelerator starts bringing new tile while he's computing on the tile that is already in the accelerator.
So by itself, the accelerator could start programming weights as the previous stripe is finishing, but the processor pipeline doesn't have the bandwidth to do that. So you have to decide which data you want to transfer in and out. You may think about different styles of integration, which would allow you to do that. I will briefly mention that in the next slides. Actually, I have plenty more to show. Let's see how fast we can go, but feel free to stop me anytime. Okay, what can we do more? So if we have a weight stationary systolic array in which we have to program tiles, and these models are deeply quantized, then it turns out that quite few of the tiles can be all zeros. And if a tile of weights is all zeros, then you can just skip the computation of the entire stripe of inputs because, yeah, you're just multiplying by 0. This is rather cool, but we have to take into account that not all of the matrix-to-matrix multiplications in a transformer are between an input and a weight. So if this is the case, and these are the operations which are in gray here, then we can do this trick. If instead we are multiplying two activation matrices, then this operation is not prunable, at least not prunable statically. So this cannot be optimized, at least not easily. Luckily enough, in practical cases, it turns out that a large portion of the matrix-to-matrix multiplications are prunable in a static sense. And this may change depending on the transformer model and also at runtime depending on the input that you are processing. So take that with as a rule of thumb and not as an hard value. So what can we do? Well, if you are the embedded system laboratory of a PFL, you just pick up your phone and phone someone in the machine learning department and ask for doing some pruning. And this is actually what we did, not internally with the PFL, but with the University of Bordeaux, especially with Colin Jean-Luc Roy, our long-term collaborator. And he said to us, look, you can actually prune quite a lot if you're smart in your pruning. You can prune a lot the encoder layers, and particularly the first layer of the encoder. We asked him, okay, why so? And he told us, look, these are the results. We're looking into it. Just deal with it. Okay, fine. So we took advantage of this ability of pruning blocks, and we encoded our matrices as sparse matrices with indexes identifying which blocks are non-sparse. And it turns out that the quality of service versus performance trade-off which you can achieve is pretty interesting. This is an example of two classes classification with sentiment analysis on INDMB. So it's a transformer which looks at the reviews of movies and tries to understand if it's positive or negative. And in this case is kind of an easy task. And this compounds atop all the other speed-up strategies which you've seen. So we can go from 90x to 170x while sacrificing 1% of accuracy. And this is with respect to the naive software implementation. As for a more complicated task, so this is speech recognition based on LibriSpeech database, we still have quite a lot of gains due to block level sparsity. So this is the runtime. You can imagine that if we don't do any pruning, our runtime will be this rectangle. Due to pruning, we can just carve out all that part. And if you look at this graph, you can see some similarity between the two, right? Oops, sorry. Please don't say that I'm finishing the battery. Okay. Any question about systolic arrays and transformers before I move on to something a little bit crazier? Okay. Analog in memory crossbars. So I spent quite a lot of time in another lecture saying that we want our in-memory computing to be digital, and now I'm contradicting myself saying, okay, let's do something analog. Why so? This is very interesting because it is a structure which allows to do matrix vector multiplications in constant time. So basically, you have these connections with programmable resistances. You input some currents, you have analog to digital converters at the output, you perform computation in analog, and at the output we have the multiplication between the currents and the resistances. This is a very naive way to describe something which is rather complicated, but I'm not here taking a technology viewpoint. There is a lot of literature about it, and I'm not sure I'm the proper person to discuss it. If you are interested, you may do worse when looking at the work of Irem Bobat, Abu Sebastian at IBM Research in Zurich, with whom we have a long-standing collaboration, and which actually provided the low-level characterization of how these crossbars behave. What we did was to see if this crossbar, as characterized by IBM, were any good in accelerating practical workloads. And again, we interface them as custom functional units with the idea that each processor has a private crossbar, and these crossbars are programmed before a model is run, and then once initialized, they are never written to. Why? Because of two reasons. The first one is that writing to a resistive memory is very expensive. And secondly, because the endurance of this type of memories is pretty low. So you don't want to write to them continuously at runtime. You want to minimize the number of writes which you do. How did we model this thing? Again, with custom instructions. In particular, an instruction which queued the input, one which dequeued the output, one which initialized the processing on the crossbar, and one at the finally which initializes the values of the variable resistances. So writing code in this way using inline pragmas is painful if you want to express a whole neural network model. So what we did was to provide a higher level library so that the user can just write something like map a matrix, queue a vector, start the processing, and queue the output. What we mapped were machine learning models from different sources, multi-layer perceptrons, which is kind of the easiest thing you can possibly map as a machine learning workload, but then also long short-term memories and some CNNs, and we mapped different layers of this workload onto different processors while accelerating their matrix vector multiplications. This is the definition of the system which we used. Again, it's pretty similar to the one which I shown you before, and this is the characterization coming from IBM. As a side note, people use different technologies to realize non-volatile memories. In this case is phase change memory, PCM. You can have different trade-offs depending on the actual physical mechanism and implementation that you use in order to realize an analog in-memory computing crossbar. And this is what we obtain. So yes, even when I finish the sentence, even with a small crossbar, you can have interesting speed-ups because we can do the computation of a tile of a matrix to vector multiplication in constant time. And if you accelerate something, then you can also have energy gains because energy is power times time. Please.
So how far in the abstraction layer do you have to go to model the crossbar itself?
So what Gen 5 is an event-driven simulator. So you have to tell to the simulator, in response to a given input, what will happen after a given number of clock cycles. So this is the level of abstraction which it gives you. For example, if you have an integer unit, you can say that if you activate that integer unit and you want to do an addition, your addition will be ready after 2 clock cycles. Something like this. Yes, please.
Since Gen 5, according to what I understood, is a system level simulator that you are trying to model the analog processing in memory, do you think we can rely on the performance that are being captured by such?
So I think that your question is how realistic are simulations while doing all this.
Exactly.
So the question is that we did our utmost best to be realistic, because this is data which is definitely real in terms of latency, in terms of energy, etc., etc. But you can very easily cheat yourself by using this type of simulators. So when you're exploring systems using something like Gen 5, you also have to say where your characterization data comes from. Other questions? Yes, please. Last one.
Last question, yeah. So when you say speed up, actually according to what you just said before, you are using phase change memory technology. So I think, according to my knowledge, it has smaller latency at the level of bits compared to, for example, DRAM. So do you think that?
So the question is, okay, so you're using PCM here, and this is a higher latency with respect to using DRAM, or in a cache you use SRAM, same thing holds. Yes, it is true, but the trick is that we're not using PCM to do storage. By and large, we use that to do computation. So we're doing computation in parallel. In particular, we're doing matrix vector multiplication in constant time. Instead of doing every multiplication, we just do all of them in parallel. This is where the speed up comes from, not from the delay of the particular cell. Okay, everything is good. So let's move on. And let's ask ourselves more questions about analog in-memory computing. So one question which we may ask is, so we always interface stuff as custom functional units. What if we instead starting to interface with AMCs as memory mapped accelerators on the bus? At this point, instead of interfacing with this accelerator in terms of custom instructions, we would use pointer to dedicated memory location, and this would control our accelerator. It is very much a trade-off between flexibility, because once we have a bunch of accelerator on the system bus, we can dynamically assign them to different cores, and raw performance, because if our accelerator sits on the bus, they are pretty far away from the processors. You have to move data back and forth. The second question is, what is the accuracy performance trade-off? Because if we have an analog accelerator, we have all sources of noise coming in, something I discussed a couple of days ago, and we have to deal with them, and this will impact the actual quality of service which we will have. First question, which coupled is best coupled paper which was accepted 2 days ago in Transaction on Parallel and Distributed Systems? And our comparison is between tight coupling custom functional units versus loose coupling memory mapped accelerator, which I can dynamically assign to different processors. And the reason why there is a trade-off is that most often than not, we will not have enough acceleration resources to cover all the operations required by a network. This is because hardware is designed before software. So if you give me some hardware, I can always design a neural network which does not fit in that hardware. Okay? So we may have different conditions like, okay, we're lucky, we have enough accelerators to cover all of our computation, or we don't have enough columns, or enough rows, or we don't have enough columns, or we don't have both enough rows and enough columns. So we have to decide how to assign our accelerators to the computation. We experimented with two different heuristics. One is a heuristic in which we try to have to distribute equally the accelerator resources among the different layers, and one in which instead we try to cover the biggest layers with accelerators before going to the next layers. So this is the results which we gather. One result is, if you compare the equal and prioritize largest layer solution, is that there is no clear winner. So I guess that we are missing something here, and maybe there is a better heuristic which can get the best of both worlds. We just didn't find it yet. The second take-home message, again, looking, for example, at this yellow line, is that sometimes having more accelerators resulted in a slowdown. Why is that? This is because if you are using a crossbar, but just a tiny little part of it, the acceleration which we have by parallelizing the computation is not worth the data movements. So at that point, you would be just better off doing things in a normal way inside your processor and don't invoke the accelerator at all. The third take-home message is that the type of integration which you may want to do is very much application dependent. If you have a lot of data reuse, so once you transfer some data to the crossbar, then you can reuse it over and over, then you're better off with a loose coupling because you can amortize the cost of data movement, and then the flexibility of being able to assign accelerators here and there pays off. And this is the case of VGG16. In the case in which you have, for example, separable convolutions, that's wise pointwise, where you have less data reuse, so being able to access your accelerator fast and having a fast communication between digital computation in processors and analog computation in crossbar is what pays off. And in this case of low data reuse, then you're better off with tight coupling. So it's very much a matter of hardware-software co-design. Any question before I move on? Yes?
Maybe I didn't hear that. Have you considered the option to have both? Have a few of them out of the core to make bigger and a smaller one inside the core?
No, because simulations are very long. So the PhD student had to graduate. We only had so much time to invest, but this is a very interesting question which we are actually considering right now. So if we see each other next year, maybe I will have a different answer. Other questions? Okay. So, Lion Earth. Surprisingly enough, if we look at the state of the art, when people are trying to implement machine learning workloads onto systems, we have, either fully digital implementations, which is the standard vanilla one, or fully analog implementation, in which, yes, we may have a lot of speed up, but what about analog noise? This is mostly not considered at all. Or we have some initial considerations about that. So in the Diana work, and I think that the author of Diana is here at the summer school, so yeah, if you find him, you can ask more about that. What they do is that they say the first and last layers are the most sensitive to noise, these are in digital, and all the rest I want to map that in the analog domain. But they don't very much investigate this assumption. So we found the low-hanging fruit, and yes, we wanted to investigate that. In order to do it, we used a optimization flow, which is very similar to what I already shown you many times. So you take a layer, you transfer it to analog, you do some fine-tuning, see what is the effect of its implementation in analog, and you decide if you want to accept the optimization move or not. This is what happens. So the moment in which a layer is transferred to analog, you have that usually your accuracy just drops like a rock. These are all these points here. But then most often, with few retrieving inputs, you are able to recover quite a lot of your accuracy. All this work relies on a characterization kit by IBM Research, which is called like this. I have no idea how you can pronounce that, but this is the name. It's available as open source. It's not our contribution from EPFL, but I think it's a very nice tool if you want to have some system-level exploration of analog crossbars. Now, we actually implemented our methodology with different workloads and different data sets, and we could see that we could have decent speed-ups while controlling accuracy, while just doing everything in analog can have disastrous results to the point in which outputs were not really usable. And the Diana strategy of mapping only the first and the last layer may have very varying results. Sometimes it works very well, sometimes it doesn't work at all. So as kind of an heuristic, it's not really what you want to do when you're mapping a workload to heterogeneous resources, because basically you don't know where you're going. So what we obtained in this case were 2.85x speed up with 5% accuracy degradation. Again, you can have many, many results in our paper. I'm now moving on to compute memories, and now I'm very scared because Onuri is actually in the room, but yeah, hopefully it will work out. So, we have seen a number of compute memories already. Actually, analog crossbars are a kind of compute memories, not really what we mean by saying a storage which also compute, but is more using storage elements to make a computing machine. Also, in other lectures, I've spoken about bit-line computing and how we can use that in order to accelerate convolutional and fully connected layers. Now we have the first implementation of compute memories that I want to cover, which is about near-DRAM computing. So why computing near the DRAM is interesting? Well, basically because this is the densest memory which we have. So if we want to have a massive amount of parallelism and to really minimize data movement, DRAM is a very interesting place to be to do some hardware-software exploration. And actually people propose near-DRAM computing at different integration levels. So this is an HBM memory. It's a type of DRAM in which you have different chiplets stacked vertically on top of each other, and on the side in the interposer you have some logic. Different way to do that is instead of having the logic on the side, you just have it at the bottom and you connect vertically to different walls. And one final solution, which is getting a lot of traction, is having computing at the periphery of each bank. Why it is interesting? Because there are many, many banks in a DRAM chip. So in this way, you may have a lot of computational parallelism. On the other hand, you're not messing up with the memory array itself, which is something which is usually very optimized for a particular technology, and it takes a lot of convincing in order to have computation happen inside the memory arrays themselves. So our stance in that was that we wanted to have a framework which allowed us to do some hardware-software co-design exploration while considering near-DRAM computing. Which means that we have to have a framework in which we can execute entire applications, at least in a simulated environment, but also in which the near-DRAM processor has a path to fabrication. So what we do is to define a near-DRAM processor as a system C module, which can be synthesized and also integrated as a component into a Gen 5 simulation, so that we have this dual nature of system simulation on one side and path to fabrication on the other. This is how our framework looks like. The inputs are architectural parameter, memory size, the parallelism, the DRAM standard, and then on the programming interface side, the user can program some assembly code which translate into DRAM commands. So we don't ask the user of the framework to punch zeros and ones, but we have at least a thin layer of abstraction on top of that. And then these commands go into a DRAM simulator, which, spoiler alert, is actually a Ramulator from the Safari group. And here we have our system C model. So again, Ramulator for the DRAM simulator and the system model for the CNN cores. This is the design of the near memory processor, which is heavily inspired by the FinDRAM processor from Samsung. So Samsung did this FinDRAM design in which there is a processor which interfaces to two different memory banks, and we just started from that point to build our template. It has a number of floating point SIMD unit, a SIMD register file, scalar register file, and a control unit which fetches data from a small instruction buffer. So this is the instruction sets which we targeted, which again is exactly like the one of FinDRAM. We have simple SIMD arithmetic operation and some control in order to do jumps and exit. This is what the assemblies looks like. Like here, I'm writing to the data memory, I'm just providing the instruction that I want to be stored into the control memory, and then I trigger the execution. This is what the user has to write as assembly code, and this is the translation into binary DRAM commands. Is this high level? No, not at all. We are working on a compiler, but it's not ready for prime time yet. So this is where we are at the moment. But what we can do with that? Well, we can do kind of interesting design space explorations. So, for example, given a workload, how many resources I want to devote to storing data, and how many resources I want to devote to storing instruction. So what is the trade-off between how big C should be, the number of control instruction, and how big R should be, the number of data register that I want to instantiate? It turns out that this is very much application dependent. If you have a lot of data reuse, you want to have more instructions. If you want less data reuse, you want to have more data. And this is kind of intuitive, if you want, but now we are able to quantify that. And this is what this graph means. Another exploration is to which type of memory we want to interface our computing elements. Because different standards have different numbers of cores per channel and SIMD lanes per cores. So at the end of the day, they support different levels of parallelism. And it turns out that this is very important in order to have both performance and efficiency when we're talking about near-DRAM computation. In particular, the GDDR5 standard, which has a lot of cores per channel and a lot of SIMD lanes which are available, can execute very fast different types of computational kernels, and this leads to quite a lot of energy efficiency. I said before that our framework as a dual nature on one side allows to do some implementation level analysis and exploration. On the other one allows to do some system level exploration. In particular, by interfacing our architectural template as a module inside Gen 5, we can write some host application code which produces memory accesses, which are then interpreted as different instructions for the near-DRAM bank processor, and we can either address all the processors at the same time or each of them individually. So, for example, if we want to execute the same program on different banks, we will program all the processors at the same time. If we want to store input data differently in between the different banks, we will just address each of the bank separately. This is very much work in progress, but is very promising, and we can see that especially if we have a decently sized workload and a decent level of data reuse, we can harness quite a lot of speed up by interfacing near-DRAM processors to a system and executing from the system some applications which is then distributed. So this is all I had to say about near-DRAM computing. Questions? Yes, please.
It's really simple. Like the near-DRAM processor has to go which clock speed? Does it the RAM clock speed or?
Yes, this depends on the actual format of the DRAM to which it is attached. I honestly don't remember from the top of my head for the different standards which is the clock frequency.
I suppose it's slower.
Yeah, it is slower, not dramatically slower than the ones which you have on system. So we're not talking about tens of megahertz, we're talking about hundreds of megahertz. Other questions? Actually, yeah, here it is. The frequency of the different standards. Other questions? Okay, so now I have to pick and choose what I want to talk to you about. So, to set the stage for the next topic, so we are entering the era of 2.5D integrations. For different reasons, we are seeing more and more systems which are composed of different chiplets connected through an interposer. The two main reasons are, one is yield. So if we have a number of defects on a wafer, the number of defective chips which you have is dependent on the size of the chip. So you can have a much larger number of working chips if you have small ones than if you have big ones. The second reason is that by using chiplets, you can mix and match different technologies depending on what you're doing. You can have a chiplet doing radio frequency things, you can have a chiplet doing analog things, you can have chiplets with different criticalities and so on and so forth. Extreme example is the Ponte Vecchio system on chip, which is a beast of a chip, is 100 billion transistors, 47 chiplets, and these 47 chiplets are fabricated in 5 different processing nodes. So this is all fine, so you can maximize your economic efficiency, you can maximize your yield, but you also have challenges due to that. And one challenge is that by having the different chiplets communicating via microbumps through a substrate, you're introducing a bottleneck on how many microbumps you can actually have, and these microbumps must be shared between the communication in between different chiplets, but also the supply of energy towards them. So there's a high competition for this. So can we do something about that? And that something is, can we have wireless communication at this level? Does it make sense? Because if we can have wireless links, then all the microbumps can be used just for control signals or for the power supply. So our question is in-package wireless viable? Again, we were not exploring the technology, but we wanted to have a system evaluation framework which used hardware-validated components in order to investigate this question for practical applications. How did we do that? We took the standard communication primitives in Gen 5, which is called the crossbar. It has nothing to do with analog crossbars. I'm sorry for overloading this word, but it's just the standard communication primitive. And then we added a MAC protocol to that in order to mimic what a wireless link would do. This is a pretty efficient solution because it allows us to decouple the actual MAC protocol to what we wanted to simulate, and also to interface wireless link at any level we wanted. We wanted that to be in between different cache levels, we could do that. Different clusters, we could do that. Main memory and level 2 cache, yes, we can just instantiate that as a communication primitive inside the configuration file of Gen 5, and it just works. As for the MAC protocol, we looked at 2 different ones. One is exponential backoff, in which masters will just start sending, and if a conflict happens, both of them stop, and they try to resend inside a window at random point inside this window, and this window exponentially increases in size as we have more conflicts, or decreases in size as we have more successful transmissions. The other protocol is token passing, so there is a virtual token which is passed among the masters, and if somebody has the token and has something to transmit, they can go ahead, otherwise they have to wait. Again, we could instantiate that anywhere, but we had to instantiate it somewhere, so we used this as a test system, so 4 clusters of 4 cores each, and we had a wireless link in between cluster at the level of level 2 cache, and one at the level of, at the level of the level 1 cache, and one at the level of the level 2 cache. As for the workload, we started super simple, so these stream workloads are just trying to exercise the wireless links as much as possible. They are the simplest application you can think about, but also in our case, kind of the worst case scenario, because nothing will use the links more than that. And then we also looked at CNNs, either mapping part of the layer in each of the core or mapping one layer into one core. So, as a baseline, we modeled a UCI interconnect which is pretty fast, but also has kind of a high latency. And why is that? Because if you have to communicate in between chiplets, you have to go from one chiplet through the silicon of the chiplet, through the microbump, in the interposer, and then back up onto the other chiplet. This link is, of course, buffered internally, but it has quite a big capacitance. So it takes quite a lot of time to communicate towards that, even with respect to using a wireless communication. And what we have seen is that, especially for the number of cores which we were talking about, something like 16 cores, 5 different wireless antennas, and so on, token passing works quite well, because passing a virtual token in between 5 antennas is pretty fast, while if we have a lot to transmit, we may have a lot of conflicts. So if we don't go to very, very high bandwidth, then exponential backoff results in a lot of retries. Here in yellow, I'm highlighting the 100 gigabit per second, which is actually the state of the art, which has been demonstrated for ultra low range wireless communication. Demonstrated means that people did a prototype of that, but not the integrated that on a 2.5D system. So there is a difference between a implementation in an SoC and a technological demonstrator. More results. So if instead of having simple application with just stream as much as possible, we have realistic applications, things go even better, and token passing actually starts to be better than wired, even at 10 gigabits per second, which is something which is pretty reasonable even in today's technology. So I think this is the last thing that I want to share with you today, and it is about that when you have a new technology or a new medium, you can just take an hard look at it and say, okay, what else this can be useful for? In-package wireless seems to be pretty nice in order to have fast links in between chiplets which do not use the microbumps. But once you have that, you can start reasoning about task mapping. If you have wires connecting different processors, you want the communication to be between cores which are physically close to each other, because the longer the wire, the longer it will take to communicate data. But if you have a wireless link, then the physical distance doesn't matter anymore as long as you're in range. So you can start thinking about distributing tasks to cores which are physically distant in order to have a better thermal behavior, because cores, they heat up and high temperatures are bad, and we want to mitigate that. So you can do a thermal aware mapping which take advantage of wireless links. And this is the whole framework which we did in order to investigate that. We started with the workloads, we did some system simulation modeling with our wireless links. We had some runtime profiling. We estimated the power from the profiling data. And from the power estimation, then we could do some thermal simulations and finally some thermal maps. Here starts a big aside about thermal simulation. So this is based on the equivalence between thermal and electric characteristics. So if you can have a good electrical simulator as a quantized finite element simulator, then you can also make a good thermal simulator out of that. You just say that the temperature is equivalent to the voltage and the heat flow is equivalent to the electric current. And you can do exactly like equivalent electrical circuits, which model the heat instead of modeling electrical characteristics. So there are a lot of thermal simulators which work on this principle, and in our lab we have developed something called 3D-ACE. The last iteration is 3.1. It is fantastic, and you can find it and download it there. How does it work? You define the geometry, and this geometry can be three-dimensional, and it can also include advanced features like liquid cooling inside a three-dimensional stack. And this is a real technology which I will not have time to cover today, but you have backup slides at the end of your handouts. And then you define the geometry, you define how each of the layers behaves, what are the material and the physical, thermal conductivity, and the heat capacity of the material, which model how the heat spreads out, and then you also have to define what are your heat sources. So one thing which is very nice about the last version of 3D-ACE is that it can work with cells which are heterogeneous in nature. So instead of dividing the three-dimensional space equally, we can have bigger cells and smaller cells. Why this is nice? First of all, because you may want to abide to the different regions precisely of your layout. So if this is a memory and this is a processor, you would like your grid to abide to that. Secondly, because you would like to have smaller cells in the parts of your chip which are more critical. Typically, memories are cooler than processors. You would like to have a finer grained analysis into processor and a coarser grained analysis onto memories from a thermal perspective. And third, because now you can model chiplets. If you have a chiplet-based system, your interposer will last for the entire system, but you will have air gaps in between the different chiplets. Air is a pretty good thermal insulator, so if you don't account for that, your thermal simulations will be completely wrong. Other things, so you can use 3D-ACE to model steady state, but you can also model transients, and you can plug in different types of heat sinks separately from the tool itself, so you can define them with OpenModelica and plug them in. So it is accurate. So red line are measured, black line are 3D-ACE. You cannot distinguish them. And it's very useful if we want to model a thermal away task mapping distribution using wireless links. We are back to square one. So what we did, we had a very simple heuristic in which as tasks come, they are mapped to the processing core, which is physically most distant to any other active core. So this is our target architecture, 4 chiplets again, and each of the chiplets we model as much as possible ARM A72 cores, and this is because there is an architecture which is chiplet based and use exactly this core, so we could use that data to do our thermal simulations. Benchmarks, and these are the thermal maps which we obtained, and hopefully you can get that. Red is back, blue is good, there is more blue here, so it works. But if you need more results, here they are. So if you have a wired solution, so UCI E is the wired, and C means cluster, TG means temperature guided, so spreading the workload to physically distant locations as much as possible. So if you do a thermally guided wired solution, your performance just goes down like a rock. Instead, if you do a thermally guided wireless-based solution, you can kind of have the best of both worlds. You can have pretty good performance, so small overhead for communication, but also low temperatures. And here is more results for different benchmarks. I will not discuss them. They are all in the paper. It just works pretty well. Now, I said that we are moving towards chiplet-based architecture. Actually, we are even moving away from that towards 3D architectures. And this is real architectures which have been proposed, which are very much 3D, and they have a lot of heat generation, and thermal issues for them is very much a challenge. Liquid cooling is something which can help, and if you have very small channels, you can actually use two different coolants, one which is a fuel and one which is an oxidant. What you can do with that, you can extract charge by using something called fuel cell arrays. So you may have cooling and also power supply at the same time. There is a complex trade-off into that because the amount of charge you can extract depends on the temperature. The hotter the liquid, the more charge you can extract, but actually temperature is something that you want also to avoid. So we made two papers driven by Halima Najibi, now Dr. Halima Najibi, which look at these trade-offs from a design perspective and from a runtime perspective. I have absolutely no time to go into that. You have the references in the slide. Just take a look. I think it's a very fascinating technology.
Sorry, just out of curiosity, is it the same as the Peltier effect?
So it's kind of the Peltier effect on chip. So now we are using the same processing which we are using to etch the metal layers on a system on chip in order to etch microchannels, micrometer wide, and then pumping liquid into that. And this is a technology which is real and it has been demonstrated. We did the system level evaluation on the impact of that technology. Spoiler alert, this is not enough to power an entire system, but is enough to just help, for example, to power all the memories in a realistic system.
So when it comes to the 7-nanometer technology, I guess MacPath is accurate in 22, isn't it, for the 7-nano design? I guess so.
So the answer is, how did you do the characterization given that MacPath gives numbers for 22 nanometer and our designs were in 7 nanometers. So actually one beauty of 3D integration is you can mix and match different technologies. So we use MacPath to model the memories which were actually in 22 nanometers.
Yeah, but the structure is kind of changed.
So this is not monolithic integration. This is one chiplet on top of the other. What you're thinking about is monolithic integration. I'm sorry if I cut you, but I'm very much out of the time, and I think that Cohen is going to kick me out very soon. So, just some conclusions, and I really have to do that. So, this is what we have seen in those 4 lectures. We have just gone around the hardware-software co-design receipt, and we have seen many, many ways in which these hardware-software co-design receipts can be applied, starting from applications and starting from very low power scenarios and going up into more complicated architectures and moving from applications to hardware and systems. In all cases, what we have seen is how we can harness opportunities from the technology's applications, and how we can address challenges from both worlds in order to co-design algorithms and computing systems. Just few messages which I may leave you with, which derive from my experience. So when dealing with something like this, you will fail a lot. I just show you a few things which turn out to be working, but there are many, many examples I can give you of things which didn't. Try to fail as early as possible. Don't put yourself in a situation in which you spend months studying something and then you realize that that something doesn't work. Find what are your hidden assumptions, because this will make you aware of what are your blind spots, and everybody has blind spots. So we are all experts of something, but we have to be aware of the things which we are not expert on and what are the implications for our own work. And if you find what are your hidden assumptions, you can also very easily keep an eye open for the next steps. We have seen examples of that. Compute memories, bitline computing. Oh, this thing is also good for error correction. Fine, I can use it. Or wireless, inter-package wireless link. Oh, this is an implication for task level mapping. I can study that. So the more you do, the more you have opportunities to advance and to innovate. Finally, there are a lot of papers on everything. If you're a PhD student, you may have an impression that everything has been solved. The fact that there are so many trials of solving the hardware-software co-design receipt means that we haven't figured it out yet. What we're seeing in the immortal words of the philosopher George Cham for PhD comics is we are just looking at the tail and we have no idea what the animal looks like. All this would not have been possible without many, many people which I had the honor to collaborate with. So let me thank them. I'm very grateful for them, very grateful to the organization for having me here. And this is the end of my cycle of lectures.